Physics time. I think I titled the one yesterday, Gravitational Interactions Part 1 or something like that. So let's call this one Gravitational Interactions Part 2. So we're still talking about gravity. What kind of gravity? What did we call it yesterday? How does gravity behave in the universe? It's the same, right? Universal gravity, right? Something, when I say the same, I mean that everything exerts a gravitational force on every other thing. Everything with mass exerts a gravitational force on every other thing with mass. We'll learn about in chapter 15 of relativity and a little bit today that light, even though light has no mass, is also affected by gravity. So really, we could say every single thing in the universe is gravitationally attracted to every other thing, right? We talked about that yesterday. The first thing we're going to talk about today is that gravity is what we call a field force, which we also sometimes call a non-contact force. We talked about these at the very beginning of the year. Do you remember that? When I say non-contact force, what does that mean to you? Yeah, it doesn't have to be physically touching. So think about some other forces. Friction, is that a non-contact force? No, the things have to be touching for there to be friction, right? If I push you down on the ground, is that a non-contact force?
That's contact.
That's contact. I have to be touching you to push you, right? It's not Star Wars. If Star Wars force was real, would that force be a contact or a non-contact force? Non-contact, right? It's not, which is probably good because it would be kind of scary. But we also call non-contact forces those that don't have to be touching. Listen, right now I am touching planet Earth, or listen, I'm touching something on planet Earth. Is gravity still acting on me? Yeah, of course it is. Just because it's non-contact doesn't mean it can't be touching. It just means it doesn't have to touch, right? These magnets are a good and classic example of a non-contact force, right? They are not touching, but they still act on each other, right? Right? Mm-hmm. But when they're touching, are they still acting on each other? Yeah, of course they are, right? They're look at that. It's weird. They're still touching, but they're still acting on each other, right? So just because it's a non-contact force doesn't mean it can't touch. It just means it's working even when it's not touching. So we can say it's not necessarily touching. Why might we call this a field force? Yeah, it surrounds the object, right? If we think about that little magnet that I just had there, this is a great drawing of that. The magnetic field of it, technically the gravitational field too, but the magnetic field of it exerts this field force in these kind of lines like that around it, where anything that I have that's susceptible to a magnetic field in this area is going to come towards it, right? Or away from it. Same thing with the gravitational force. So the Earth exerts a gravitational force as a field all around it. How far out should these arrows go? Technically. Forever. Infinitely, right? Technically infinite. But we do know also what happens the further away it gets. The weaker it is. We could graph the force of gravity. What should we put on the y-axis probably? Let's put newtons, the strength of gravity, right? F sub g in newtons. What should we put on the x-axis? I'm talking about how distance affects it. So
infinity.
Distance, and we're going to measure distance in meters. The further away we get, what happens to the force of gravity? Smaller. In fact, because it's a square, it forms this shape of graph. Do you know what this is called in mathematics? It never, ever, no matter how far away we get, it never actually gets to zero. What do we call that in math? Do you know?
What we did about last year.
This is the first letter. Do you know it? Asymptote. An asymptote. It approaches zero but never actually gets to zero. It never ever reaches zero. So even if I'm 15 million light years away, the Earth is still technically affecting me gravitationally. It cannot be measured, right? It's so minute. Even after only a few 100 million meters, it's very, very minute. But the Earth's gravitational field is technically infinite. It just tapers off pretty quickly. Same thing with these magnets, right? If I have them fairly close to each other, look at that. If I have them fairly close to each other, it'll resist, or it'll go against gravity and pull it up. But if I have one on my podium, is this one still technically attracting this one? Mm-hmm. Yeah, technically, but it's not strong enough to make it move, right? It has to be actually quite close for it to be strong enough to make it move, because magnetism works in the same way. The further away it is, the weaker the force of gravity, the weaker the force of magnetism. We call this a field force. So both gravity and magnets are field forces, yes.
When you had all of those compasses and then you moved the magnet.
Yeah, right. Because in fact, what we did, Morgan's talking about, we had compasses, and we'll do more about magnetism later in the year, but we had, if there's time, but we had compasses kind of scattered about around a magnet, and all their little arrows pointed right along the magnetic field line. So one up here might point like that. And it was kind of a neat way to visualize a magnetic field. Gravitational fields are easier because they're only attractive. The reason a magnetic field looks this way is because magnets can be both attractive and repulsive, depending on what side a magnet is turned to. But since gravity is only attractive, it's spherical. Everything is pulled in at the exact same rate. I'm going to erase this and we're going to move on. So what happens if, let's think about a little thought experiment here. If we had, you ever, when you were a little kid or something and you're digging in the garden, you ever dig when you were a kid? Is that something I only did? And your mom said, don't do that, you're going to dig to
China?
To China. She probably said, you're going to dig to China. You weren't, because China is not right across the globe. You would have, if you could do that, you couldn't. But if you could, you would have dug into the Pacific Ocean. But imagine for a second that we do have a hole going all the way through planet Earth, okay? And we're going to jump into the hole. We're going to disregard that you were a tenth the size of Earth, and that you would vaporize instantly when you got into the core because the temperatures were so high. We're just going to imagine it's just a little.
You're in the astronaut suit and all that.
Yeah. You're going to be fine. So you jump through the hole. Let's say you're right here, right on the surface. You're level with the surface. How is gravity affecting you? It's not a trick question. Yeah, it's just pulling you down towards the center like it always does, right? The deeper we go in the hole, though,
the stronger it gets.
Yeah, we get nearer the core, so the force of gravity gets stronger. But what else? Look, now not only is there a significant amount of mass below you, but there's also all this mass above you, right? Mm-hmm. You see that? And so the further we get, the closer we get to the core, in fact, when we're right at the core, where are we being pulled gravitationally?
Down.
Yeah, just to the core, but we're also being pulled by all the mass around planet Earth. And so there's actually, we said yesterday that we don't actually experience zero gravity in space because we're still being pulled towards Earth. We just feel like that, right? But if you're in the core of a planet, there actually is exactly zero gravity. There's no gravitational field there because it's all evened out by the mass around it, right? So as you jump in, what are you going to be doing? What's your speed? Yeah, well, we're going to talk about it in a second. But as you jump in, what's your speed doing the closer you get?
Faster and faster.
Faster. And when you get to here, now as you're zero gravity, so there's no force on you, but you're still moving, right? You're accelerating, but now as you come out the other side, you're accelerating which way?
Slowing down.
Yeah, you're accelerating still towards the core, which means you're slowing down. And so actually it turns out that when you get to the other side of the planet, can you guess what will your speed be relative to your speed here? The same. So whatever speed you jumped in with, you'll have just that much speed coming out, of course negating friction, negating that you would vaporize, negating that a hole like this couldn't even exist because it would collapse on itself. But all those things aside, you would come out the exact same speed because gravity is pulling you the other direction. Because there's more and more planet on the other side of you the further away you get. Does that kind of make sense? Mm-hmm. Do you have questions about this? Because gravity is a field. So if you were to teleport in a magic space bubble that would allow you not to be vaporized, if you were to teleport right now into the center of the planet, there's zero gravity. You'd just be like, oh wow, ooh, neat. It's really hot. I'm going to throw up. For a couple reasons. We talked a little bit about this yesterday too, but when you're in a car, we're moving on to the next thing now. Do you have questions about this before we do? When you're in a car and you are going over a hill, for a second, but this is a really good looking car, you feel the little tummy thing, and that's because you're up in the air, right? And we said yesterday it's because it's not that there's no gravity. Of course there's still gravity, but what's missing that you don't feel? What other force? No, you might feel that. What other force do you not feel that you're used to feeling? We said yesterday that when I just stand here, it's not really gravity that I'm feeling. I'm feeling what? What's actually acting on my body, pushing me upward? The normal force, right? The normal force. So when you're going over this little jump, this is a good car. When you're going over the little jump, the normal force is gone, so you feel for a second weightless, right? We talked about that yesterday.
Oh yeah.
It's the same thing if you look at the little elevator lady, because she has an acceleration. So we have these 4 drawings of elevators. When the elevator is stopped, we're going to have a scale on the bottom of our elevator, right? When the elevator is stopped, what would the scale read compared to what it normally reads?
The what?
You have a scale on the bottom of this elevator. When the elevator is just sitting there, compared to how it normally reads, how will the scale read? Just same, right? If we're instead moving, if the elevator is accelerating upward, what will the scale read? More, right? Because really now, instead of just the floor pushing into you with the normal force as normal, there's also the acceleration of the elevator going up.
Can we
So there's
try
more
it?
force. Well, yeah, actually let's do, but not right this second because we're trying to learn. So then, obviously, if it's going down instead, less. So this will be more, this will be less, this obviously will be equal. If it's going down really fast, so if the elevator is dropping, right, there's no support, what will the scale read?
0.
Nothing. No weight, right? You technically, just like you were in the car, and just like the astronauts in the ISS, you'd be in free fall, and so you'd be weightless, right? You'd feel weightless. We call this weightlessness. Some people, even at NASA, they'll call this 0G or 0 gravity. That's not technically true, right? You feel weightless because of the lack of normal force, in the same way that the astronauts feel weightless because of the lack of the normal force. Last thing we're going to talk about, I do want you to learn about black holes, so read about black holes on your own. They are fascinating, but I think they're fascinating enough that if you read about them, I think you'll get all the information you need. If you want to look up black holes on the internet, you can do that. But we're going to talk about tides real quick before we finish this. You know what causes tides on planet Earth? You've heard of this before. The moon. The moon causes tides. Have you ever thought about why the moon and not the sun?
Because it's closer.
Exactly. I don't know. Did you already know that, or did you learn it from your physics book?
Already.
You already knew that. Good. All a tide is what we call tidal forces. This is in physics and in astrophysics. What we call tidal forces are not just like the tides, like the ocean tides, but it's what we call any difference in gravity from one end of a body to another. For instance, think back, we had a question on a chapter review a while ago about you're in a rotating space pod, right, around this, you remember the question like this, so this thing's going to be rotating to simulate gravity, right? So if at your feet it said you have 1g, and at your head, it said you could withstand 100th of a g difference between your head and your feet. In the problem, it was 0.5 g at your head. The reason that this is uncomfortable is because of these, because there's a difference in gravity, right? So even though in this case it's not actually gravity causing this, we feel a difference in acceleration, and that's uncomfortable. So this would count as kind of like a pseudo-tidal force. So because as you said, because the moon is closer to planet Earth, since tidal forces are all about the difference in gravity, even though the sun's gravity is significantly stronger, there's not going to be that much difference compared to the distance from the sun to the Earth. There's not going to be that much distance from one end of the Earth to the other, right? So obviously this isn't to scale, but the sun's gravity might be 1/1000th of its strength from one end of the Earth different from the other end. Whereas the moon's might be 1/20th different from one end of the Earth to the other. Those are made up numbers, but it might be that way. It's less is the point. Because the moon is closer, even though it has less gravity, there's a greater difference in gravity. And that causes tides. And the tidal bulges go along with the moon. Where do the tides form? You know about the tides happening in the oceans, right? Mm-hmm. You know about ocean tides, but you don't feel them and you don't notice them. But the land also, every single day, the land raises about 20 to 30 meters different from where it was at the equator, from where it was on the other, when the moon's on the other side. There can be a huge difference in land motion. We just don't notice it as much because it's not as strong as the liquid movement of the oceans. So the land moves as well. The whole Earth is pulled. Yeah. The whole Earth is pulled depending on where the moon is. It's obvious to us that this side that faces the moon would have a high tide, but the other side has a high tide too. Do you know why that might be?
What?
When the moon's here, the tides are experienced, high tide is experienced on the side facing the moon and the side opposite the moon.
Is that like an equal, or
Is that from like the field?
It's from the spin of the Earth. Whoop, whoop. Circus video. It's from the spin of the Earth. So it's because the Earth is spinning, that tide gets, I don't know, evened out. In the same way that like Luigi spinning the pizza crust, it evens out on both sides. In the same way that the spin of the Earth itself, we said, squishes the Earth, does the same thing with the tides. So the tide happens on the side facing the moon and the side away from it. And then the side perpendicular to the moon, both sides, this side and the other side inside the board, see, I'm acting like this is a sphere, those will have low tide. Does that kind of make sense? One last thing about tidal forces before we finish the video altogether is that I think this is really neat. If imagine instead of the moon here, the exact same distance away we had Jupiter. Forget about the sun. The sun's obviously not bigger than or smaller than Jupiter. Imagine we have Jupiter, which is bigger than planet Earth, right? Same distance away. Are the tides going to be weaker or stronger? First of all,
Stronger.
much, much, much stronger. In fact, they'll be so strong that some planets become, if it's stronger than like the Earth and the Moon, they can become what's called tidally locked. In fact, the Moon is tidally locked to the Earth.
Excuse interruption due to a
So if the tidal forces are strong enough, the Moon, like it is to the Earth, can become tidally locked, which just means that the one face of the Moon will always face that side of the planet. That's called tidal locking. But if they're even stronger, like this has happened to Saturn's moon, we have evidence of it, the whole planet will disintegrate. It'll come in half because the tidal forces are so strong. And then those halves will be broken in half, and those halves will be broken in half, and the big planet will get a what? Can you guess? If it's got all this little debris of a planet that got crashed by tidal forces around it, it might form a ring. Is that what you said? Nope. I thought you did, and now I gave it away. That's why Saturn has rings. It's widely understood that the reason Saturn has rings is because one of its moons in the past was so near to Saturn that the tidal forces pulled it apart and it became a debris field instead, and then the debris field took on the circular shape to match its orbit.
That's pretty cool.
Which is pretty cool. We now believe that when the moon first formed from a collision where another planet collided with Earth, there would have been a ring system around Earth for several thousand years when that first happened too, which would have been pretty cool, but not anymore. That's not the way it is anymore. Do you have questions about tides? Do you have questions about weightlessness? Do you have questions about field forces? Do you have questions about this thing about the Earth having a hole in it? All right, bye.